So today and the next lecture we'll look at design of the SRAM cell. Today we'll largely focus on the read of the cell, and the next lecture we'll look at the write for the cell. So the 6 transistor cell basically consists of 2 back-to-back inverters, and which have these 2 access devices which allow you to connect to the internal nodes of the cell. Because there are 2 back-to-back inverters, there are basically 2 stable states, 0, 1 or 1, 0. So as long as you supply power to the cell, it retains the state. So this connection out here in the top is where power is supplied. Okay, V cell. It's not shown in the diagram, but this is where you supply the power to the cell. Now, when you, as we discussed in the last class, let us say the node Q has voltage 0 and Q bar has a voltage of VDD. Okay, in this example, VDD is 1. Let's look at the read axis again. So the word line is initially 0. That means these 2 access devices are off. They are NMOS, so they are off. So the internal nodes of the cell are disconnected from the bit lines. Remember, in this column, this is called a column, there are number of cells in this column. So the default state is none of the word lines are on, all the word lines are off. So none of the cells are connected to the bit lines. They are all disconnected. Now, before doing a read, before accessing the cell, what is done is you pre-charge the bit lines. You take the bit lines and charge them up to VDD voltage. And then, meanwhile, you also do your decoding and you turn on the word line. So the word line goes from 0 to 1. What that does is these access devices A1 and A2 are turned on or enabled. Now QB is 1 and bit bar is also 1. So nothing happens on this side. Okay, other than you see QB goes up a little bit. Why does this happen? Exactly, because of some capacitance out here, the CGD, gate to drain capacitance, between the gate and the drain out here. When this word line goes high, this coupling capacitance causes this voltage also to go up a little bit. So that's why it goes up. Now on this side, Q is 0. So when A1 turns on, the bit line starts getting discharged. And that's what happens. The bit line voltage starts falling. Remember, the bit lines after pre-charge, they are let go. Nothing is holding the bit lines. So they are dynamic. They are like floating capacitors. And so as current flows, this voltage on this capacitor, the bit line capacitor, starts reducing because you are taking away charge, so it starts discharging. Now, of course, to complete the read operation, you will have maybe an inverter out here, which, initially the output of the inverter is 0 because both the bit line input is high, but as the bit line falls below a certain value, the output of the inverter goes high. Depending on the data value, whichever is 0, if Q is 0, bit goes to 0. If Q bar is 0, bit bar goes to 0. So you can get the data. Now one thing you notice out here, so here you basically have these labelings D, A and P. So A is called the access transistor because you are accessing the cell through that transistor. D is called the driver transistor because it's really involved in driving this node, the bit line, to 0 because of D. And P is the pull-up transistor, the PMOS. Okay, P1 and P2 are the pull-up transistors. Now one important thing you notice out here is that as the bit line starts discharging, you see this voltage Q, voltage at node Q. It goes up a little bit. There's a small bump. Why? Because if you have to support any current, you need to have a VDS in this transistor D1. Remember, Q is 0. That means input to D1 is high. That is, Q bar is high. So VDD is here. So this is on. But if I want to have any current, VDS has to become bigger than 0. The other way of looking at it is, as if you have any current, I times R, there is some voltage drop. Okay. So this voltage bump is very important because that makes a difference between a successful read and a failed read. What do we mean by failed read? A failed read is one, a successful read is one where, again, we are looking at these node voltages. These are labeled 0, V0 and V1. When I am reading, V1, nothing much happens to V1. So unfortunately here it's mirrored. So on the right side is the node, the voltage is 0. So I'm also calling it the node 0. So the node 0, which is the Q from the previous slide, goes up by a small amount, and of course the bit line discharges, in this case bit bar discharges, and you get the data out, and then when the word line is shut off, everything gets restored back to what it was before. Okay, V0 goes back, V1 remains where it is. Now the problem is, if V0 goes up too high, okay, because say in this example, this initially had the node voltage 0, because you're storing a 0 here and of course 1 is here, and bit bar was 1, and when you turn it on, this starts discharging. As it starts discharging, this node voltage has to go up a little bit to support that current, VDS. But if it goes up, what happens? Remember, this voltage is the input to this inverter. If it goes up too much, that inverter output can go down. You can trip that inverter, which will then, when this comes down, this becomes, see, when this goes up, this voltage starts coming down. That voltage is the input to this transistor again. So that transistor becomes more and more resistive in some sense. So that causes more voltage to go even further up. And it can happen that the whole thing swings and you flip the cell. Okay, so that is where the cell is unstable. You read the cell and you change the contents of the cell, because this voltage which was developed across this driver transistor is too high. It causes the other inverter to trip. Now if you know for sure all the time you flip, every time you touch it, it flips, then also it is okay in some sense. You can live with that because it's deterministic, you know. So you can account for that in your computation. It's kind of messy, you don't want it, but maybe you could live with it. But problem is, something like this is kind of very random. Okay, because maybe when you read it once, it goes up, but it's not enough to trip this. But next time you read it, it goes up, but there is some other noise event which causes it to kind of go push it a little bit more, and then the whole thing flips. So this random flipping is definitely not a fun thing to deal with, right? So it basically doesn't work. So this is something which you have to avoid. When you read the cell, there has to be determinism. Either the cell content, you basically need to know what happens to the cell content. We'll see when we study DRAMs, when you read the cell, you destroy the cell content. But it always happens, so you know. So you deal with it in the circuit design. You'll see how that is dealt. You cannot have this random destruction or flipping of bits. So an unstable cell can lead to this kind of a problem.
So we can mitigate this effect by having higher threshold voltage.
So we'll see next how we can design a cell which is robust to read, and then the next lecture we'll see how we can design a cell to make it robust to failure in write. I mean, analogously, we'll see, when you try to write, it can happen that the cell fails to write. Okay, that can happen. So that is a failure to write. Now, what is a condition for a stable read? So you probably now have a clue as to what you need to do to prevent the cell from flipping when you do a read. Basically, what you need to ensure is that this voltage on the 0 side shouldn't bump up too much during a read. If you keep it, if it doesn't go up too much, then you won't trip this inverter, and so the state will not change. So really what you want is the drive strength of this driver transistor should be much larger than the drive strength of the access transistor. So that is one relationship which has to be maintained. Now what determines the drive strength? Mobility, Cox, I missed out, WD by LD, because when you start off the cell is in saturation. Okay, and then V cell minus VTHC. V cell is the supply voltage. The gate voltage of this transistor is coming, because this transistor's gate is coming from this inverter. This inverter's output is 1, which is essentially driven by the voltage value is whatever is the voltage value of this cell, V cell, minus the threshold voltage of this transistor. So raised to whatever, the alpha between 1 and 2. So this current drive should be much bigger than the current for this transistor, right, at the same voltages. So then you know that what that means is that the the VDS required to support a particular current is not much. Okay, here actually I should have put VDS also, then it would have been clearer. 1 plus VDS. Similarly, both here, the VDS for this and this is a little different, because when you start off, this has a complete VDD of VDS, because this voltage is VDD, this voltage is 0, whereas this guy's VDS is close to 0. So when you make this bigger than this, much bigger than this, even for a very small VDS, this current will become same as this current, even though it has a larger VDS. So that is basically the intent of this equation. So usually it turns out the heuristic used is that you make this driver about 2.5, 3, maybe 3.5 times bigger than that of the access transistor. Because there is another constraint, which is the size constraint. You really want the memory cell to be as small as possible, because you will have millions of these memory cells. So if you have any savings in area, you get tremendous savings in your chip for area. And area is equal to money, is the cost. So it's very important to reduce area. So yeah. So absolutely, because what we are talking of here is, see, because one thing you can say is that, look, I'll make my D to be very large, I'll be very safe, but you can't, as I said, you can't make it too large, the driver transistor, because it increases the area of the cell. Now, of course, the benefit of making things large is you also have large drive currents, so speed can become bigger. Okay, but it turns out that also it's not necessarily the case that large cells lead to large low delays, because if I have the same size memory, if my cell area is large, then the overall size of the memory also becomes very large. So the wires also become very long. So yeah, wiring delay goes up. So it's not like a very straightforward thing to say, just increasing the size will work. But in general, increasing the size increases the drive strength. So you can expect some reduction in the delay. But it's kind of more important to have more number of bits. So even from a system perspective, more bits helps to improve the overall system performance. For example, when you have something like caches, again, maybe if you have very large caches, there's something called a miss rate. You'll have lower miss rate. That means there's more likelihood of finding information in your cache. Even though, so the cost of going outside the chip to fetch information is much higher than fetching it from inside the chip. So again, it's very important to have as many bits as possible in the chip. So usually for memories, the sizing of the memory cell is driven only by consideration of reducing the size to be as small as possible. Of course, the cell has to be stable, and so for making sure that cell doesn't flip during a read, you make sure that the driver transistor is sized such that the drive strength of the driver is much bigger than that of the access devices. Now, how do you improve the drive strength? So that you already have clues from this equation out here. And so what are the things you could do, right? So you can increase WD compared to WA. Let us say everything is the same to begin with. Now you want to improve this. So you can increase the size of the width of the transistors. Okay, that is one. You can reduce the threshold. Now what is the problem with reducing the threshold? Leakage. And that is a very, very big problem, because you will have multi-million cells like this. So you cannot afford to have too much leakage in these cells. The leakage has to be kept as small as possible. So you kind of want to have larger threshold voltages. And pardon? Right. So correct. So now the question is, why not increase threshold of A compared to threshold of you say you have some nominal threshold, then you say, okay, I'm going to increase the threshold of A. Okay, that is one possibility. What other things you could do? Different supply voltages. What supply voltage will you use for the cell? Higher than that of the word line. Now the word line, remember, is finally there will be one simple inverter driving this word line. So the supply voltage to that inverter is what is VWL. Okay, so if you reduce VWL related to V cell, again you can weaken this. Okay, what else can you do? Channel length. Do you increase or decrease? And which one? Right, so I mean from this equation it seems you should increase the channel length of A so that you weaken it further. Of course, remember with this short channel and reverse short channel effects, you can end up with some problems, so you have to be careful about that. So typically you keep the channel lengths to be the same, the minimum. Okay, again, anytime you increase the size of something, it increases the size of the cell area. So you have to keep that in mind. And so you have those options available. If you don't want to mess around with supply voltages, then the only variable you have, and you don't want to mess around with threshold voltages, then the only variable you have is width. So you make the width of the driver to be 2.5 or 3 times the width of the axis. But if you could also play around with the supply voltages, then you can reduce the width, keep the width small for the driver, but increase the supply voltage of the cell. That way you keep the area small, but have a larger supply voltage for the cell. Okay, that is something you can do. Now, there was a suggestion of increasing the threshold voltage of the access device. The benefit of that is that it helps to reduce the leakage also. One thing you should remember is that when you have a cell, when you have a column like this, typically these memory columns could be 128. Then there could be 128 cells in a column, maybe 2 to 6 cells. So when you access a particular cell, say a particular row, rest of the rows are off. Okay, but consider a row which is off. Let us assume that this row is off now. That means this voltage is 0. So this transistor is supposed to be off. But suppose let us say every other cell in this column had a 0 here and a 1 here. Okay, it had the opposite data. Every other cell. Now wherever there is a 0, and remember the bit line is 1. Just for a moment, imagine this situation when the word line is off and this is 0. Bit bar is 1. You will have some leakage, subthreshold leakage here, right, through this cell. So now imagine you are reading this cell, but then all the other cells in the column have an opposite data stored in them. Okay, so then all of them on this side, even though this cell is not pulling a current, the others, all remaining 127, 255, how many ever you have, will start pulling current from that cell. So what is happening is bit and bit bar both will start dropping. So you have to, that puts a constraint on two things. One is the leakage allowed in this access device. You don't want too much leakage because it can mess up with the operation of the memory. Because if this bit also falls, maybe if it falls at a rate faster than bit bar, then you will get the wrong data. Right, so that you don't know. Second, the number of cells you can put in a column. Say you have leakage, but then you can reduce. Instead of putting 128, you can say I'll put only 16. So this worst case condition you have basically reduced because of adjusting the number of cells. When you put fewer number of cells in the column, for each column you have this circuitry, right, to sense, to write and so on. So you are increasing that because every time you partition the memory, you start off with a monolithic memory array, say a million bits in a single rectangular array or square array. 1000 by 1000 cells. Now you have only the circuitry in the peripheral of the array. Decoders to decode and select, and then the circuitry in the column. Every time you break the memory, say instead of having 1024 by 1024, you say I'm going to have 1024 and with two pieces, 512 by 512. So you have an additional, you have broken the memory horizontally and there are two rectangular slabs now. You have to have additional circuitry for each slab. So you start increasing area overhead. As you start partitioning and making smaller and smaller memory subarrays, you will increase partitioning area overhead. Overall area goes up. So again, there is an optimum how much you should partition.
Is it like each cell will have individual bit and bit bar? Right?
No. Each cell will not have. Remember that this bit and bit bar are going vertically, all the cells in a column will be connected to the same bit and bit bar.
But we want to write, they are writing through bit and bit bar. So
Remember for
we need
the
to write differently for different cells.
correct. So see, remember there are cells in the row. In a given row, every cell will have its own bit bar pair. Okay, in a row along this horizontal direction. But all of them share the word line. So you access all the cells in a row simultaneously, but you are accessing all the columns in parallel. Okay, so there are so many columns in parallel. But within a column, all the cells are connected to the same bit bar pair. They share that. It's like one giant multiplexer. Really, what you have is a big giant multiplexer. This access device is helping you to implement a multiplexer, right? Because you're selecting from one out of n rows. You activate one row, and then that transistor is turned on and it pulls it down. So it's a very specially designed multiplexer where you have only a NMOS pass gate. You could have a full PMOS transmission gate, NMOS PMOS pair based multiplexer, but that increases the area overhead. Remember, again, we want to keep area small. So we have done away with the PMOS for this.
Will you explain the threshold?
So now let's come back to this. Now the threshold voltage you could increase for access device, which benefits from the point of view of leakage and also allowing you to put more cells in a column because the leakage is less. Remember, if you put too many cells in a column, you could have a worst case data pattern where the rest of the bits in that column are opposite to the bit you are reading, and so it will the leakage subthreshold leakage to the access device can mess up the data you see in bit and bit bar. So more threshold for the access is good from that perspective. But what happens is that if you increase the threshold voltage of the access device, the current you can pull from the bit line is determined by the current to the access device. So the current, what is called I cell, the cell current, the read current becomes small. So it takes longer for you to do the read. So you take a hit in the read time. We'll also see when we study the writes in the next lecture. You don't want to make this access device too weak, too feeble, okay, because it will help, it goes again, you can't then do a proper write. So there are multi-sided constraints to the design of the SRAM cell. Okay, everything is kind of coupled together. So you have to look at all these factors and design the SRAM cell. So typically SRAM cells are designed by specialists in these foundries. They will sit and design these SRAM cells, and very rarely do people design their own cells. You just take those cells and then you can use it, because those cells which are designed by the foundry, they have gone through all these considerations and then they come up with the design and the layout. And when they do the layout also, certain special exemptions are given to them so that they can squeeze the area down as much as possible. So all that is done and then it's tested out and so on, and so you have this finished SRAM cell which you use. But if you ever were to design your own SRAM cell, it might happen. Maybe there are some special conditions when you have, where you have to design your own cell. Then you have to take into account all these considerations: stability during reads and writes, noise margins, and so on. So now this idea of noise margin can be quantified. What we have looked so far is just an intuitive understanding as to why you have a problem, that the zero node kind of bumps up and causes, if it bumps up too much, it causes a flipping of the cell. Now the way you basically deal with kind of quantitatively analyze this noise margin is to do a DC transfer curve. Right? This is something we looked at very early in the first or second lecture, I think. DC transfer curve. So what you do is you look at the cell when you're doing a read. When you do a read, you turn on the access. You have these two inverters which are coupled back to back. You have these two access devices where you have the word line which is turned them on. So I have just indicated them here by the gate connected to the high supply. Similarly, the bit lines are also pre-charged high. So as soon as you turn it on, both the bit lines are at VDD, both the gates are at VDD. Now what you do is you take this and you cut the cell like this. You make a half cell. So a half cell consists of an inverter with this access device connected in the output connected to VDD. Okay, now you look at the VI versus VO DC transfer curve. So you plot VI and then you have VO. So when VI is 0, VO is 1. There's nothing magic there. But as Vi starts increasing, you have output falling. And remember, for an inverter, the output fell all the way to ground. Right? If you recall the DC transfer curve for the inverter. Whereas here, the output doesn't go all the way to ground, it gets stuck here. Why? Because when Vi is high, this PMOS is off, of course, but then you have this in parallel. This access device is on. For the DC transfer curve analysis, basically what you have is the PMOS here is off, but this access is on. So this access device fights with the pull down driver device, and so you have the output voltage doesn't go all the way to ground. Clearly you want this voltage to go, so now you have this curve out here for this in half cell. Similarly you do the curve for the other half cell. Now this eye opening gives an indication of the robustness of the cell. So this is called a butterfly diagram because it looks like the wings of the patterns on the wings of a butterfly. So it's called a butterfly diagram. If both the half cells were similar to each other, then you will have symmetry about this 45-degree line. Everything will look the same. But usually you will have some mismatches, and so the static noise margin SNM is the smallest eye opening. Okay, whichever is the smallest, that is defined as the static noise margin. What do I mean by that? You try to put a square out here, embed a square. The length of the square is defined to be the static noise margin. Remember, the units are in voltages, so the noise margin is defined in terms of voltage. The idea is that any noise which closes the eye will cause the cell to flip. So you have the size of the eye in some sense indicates how much noise you are able to tolerate. You have to keep the eye open. Okay, so this analysis is usually done when a cell is designed. We have to do this analysis. We have to break it up into half cell and then do a DC transfer curve analysis of the half cell, then calculate this. And then you do this analysis across all different conditions, because especially when you make the cell and you want to, when you have millions of cells, every cell should work, every SRAM cells. And you remember the cells, transistor to transistor, there will be variations. Across chips, there will be variations. All those variations have to be accounted for. So usually what is done is a statistical, what is called a Monte Carlo analysis is done. In a Monte Carlo simulation, you run the simulation multiple times, but each time you do a simulation run, the parameters are changed by some random perturbation. Usually parameters like threshold voltages and so on will have some kind of a normal or Gaussian distribution. There will be a mean threshold voltage and there will be some variation. So you sample whatever parameters are, the foundry will say these are all the random parameters. They will give you the sigma, right, the standard deviation. Then you take that, then you run multiple simulations with different values sampled from the distributions for these parameters. So that is a Monte Carlo. And then you get, for each run you get this DC transfer curve, you record the minimum eye opening. So when you do it over thousands and thousands of runs, you have to do enough runs, then you get a distribution of the statistical noise margin. Okay, then you have to say, okay, is that cell design? You designed a cell with these sizes and for these voltages, but when you do this statistical Monte Carlo analysis, what you expect is a certain mean noise margin SNM and a certain sigma. So you have to make sure that you have enough. Typically, because you have millions of cells, you have to ensure plus minus maybe 5 sigma, right? The mean minus 5 sigma still is a positive number. If the noise margin minus 5 sigma is not a positive number, what it means is some small fraction of the cells could have 0 or less noise margin. That means they will not work. So like that, you have to basically do a statistical analysis for the cell. For every design, you say I'm going to use my V cell to be 1 volt, V word line to be 0.7 volts. Then you have to do this and see is that good enough. You have enough percentage of cells which will have positive noise margin. All that is done by the foundry usually, and then you get the cell. So you don't have to worry about that. But if you were to design your own cell, then you basically do it. Now, what I'm saying is that these rules of thumbs, like what I said, driver transistor usually 3x and so on. So when you use those rules of thumb you end up with a design which will work most of the time. But when you deviate from that because you want to maybe push something, you want to reduce the area or something, you say, okay, 3x larger area, I'm going to take 1.5x, but I'm going to change the cell voltage a little bit to account for that. Then you better do all this analysis to ensure that you get the right yields. Now, what we looked at was, see, during a read, I turn on these two access devices, right? But when I'm not reading, the cell is just holding the state. When you're not reading, what are you doing? Both the access devices are off. So you just have two back-to-back inverters in isolation. Okay, and it's supposed to hold information. But even that, you have to do a noise margin analysis. So here, if you see, the distinguishing feature is that, so just ignore this stuff out here, okay? Because I cut and pasted from, because there's something, just for simulation we do this. But this, just focus on this XY, and you have the same DC transfer curve, except now you see, because I'm not reading the cell, that access device is not degrading the value, it's just holding. So here when input goes all the way to VDD, output does go all the way to ground. So the whole noise margin, the I's will be bigger, because when it's out here, it goes all the way to ground, it doesn't go up. In the case when I'm doing a read, it doesn't go all the way down, it kind of comes up like this. So the I opening is smaller when you're doing a read, but it's larger when you're doing a hold. So the whole noise margin is always, at least as much as the read noise margin. But even hold noise margin is important, because some noise could perturb and collapse this eye. Okay, we'll see an example of a noise event in a few slides. So how do we improve the noise margin? You come back to this equation. So we already said increase WD by LD or WA by LA. If you keep LD and LA to be minimum, that is the channel length, then you play around with the sizes. You can increase the cell voltage. Okay. You can reduce the word line voltage. Of course, when you reduce the word line voltage, it has a implication firstly of speed, because the cell current is determined by this cell, this transistor. That current will be smaller and it will take longer to discharge the bit line. Things will slow down. And we'll also see when we do the write, it can degrade the write noise margin. So there's a two-sided constraint. Then you can increase the threshold voltages. See, when these are leaky, these curves will be a little sloppy, but when there are large threshold voltages, you'll have nice rectangular looking curves. Okay. Now here is a more radical idea. Okay, so which is, don't allow read current through the cell. See, the problem which is happening here is that when I turn on the word line, my current is flowing through the cell, which is causing an IR drop, and this voltage goes up. So the question is, can I read the cell without having any current go through it? So then the cell is always in this hold state. So the read noise margin is the same as the hold noise margin, because I don't have any current going through the internals of the cell. Okay, so this is done. Let me come here. So one way of doing that is to put two additional transistors. So now what is done is you have an additional bit line. Okay. Let's ignore the, so then you have this pair of bit lines. So this is the same 6 transistor cell. Now you have an additional pair of transistors here. So what is happening is that this transistor's gate is coming from the internal node of the cell. And this is the access device. Now there is another word line for the read, called the read word line, and then you have the read bit line. So now what you do, you precharge the bit line, which is just the read bit line, and then when I want to read a cell, I turn on the read word line. So this transistor turns on. If this voltage is 0, there is no current. The bit line remains floating at VDD. But if this voltage is 1, then this discharges and the bit line falls. So you can you can transfer the data from within the cell to this bit line. Of course, now you see, what you have done is you have increased the area. But the cell current no longer flows through, it just flows out here. It doesn't disturb the cell. So the noise margin of this cell is as much as during read is the same as that during hold. So it has better noise margin. Cost is you have extra area, because you have 2 extra transistors, 1 extra vertical wire and 1 extra horizontal wire. Of course, this does give you 2-ported operation. If I had 2 different decoders, I could do write and read at the same time, as long as they are in 2 different rows. Okay, so I can have a dual ported memory with this structure.
What if you want to read this left-sided transistor, like 0 if it is
See, if it is 0 here and 1 here, okay, let's look at if it's 0 here and 1 here. So if it's 0 here, this is 0, so this is off, so this remains at 1. Whereas if this is 1 here and 0 here, this 1 turns it on and discharges it. Discharge only happens through here. Remember, when we do a read, the right word line is kept 0. So we don't access the cell at all during a read, the internals of the cell. Only from one side, exactly. From the through this read buffer, it is called a buffer out here. It's called a read buffer. So you are buffering.
So instead, so by changing this, in the inverter we have MOS and PMOS. So by changing the WL values of these two, we can shape this output by input graph.
By changing which one?
W by L of NMOS and PMOS.
This one.
So the shape of this graph is.
Okay. So the question is, why not also look at changing the W by L and correct.
In
Read SNM. Right. So the question is, can we do something with the sizing of this inverter and do something to this graph? Remember, when we change the strengths of the PMOS and NMOS relatively, what you're doing is you're skewing. You're pushing instead of this, the transition like this. If you make the NMOS strong, what will happen is this will move to the left. Okay. Now it turns out that we'll see in the next lecture the PMOSs are made really weak. Okay, so these are really skewed inverters.
In one inverter we have to strengthen the NMOS. In another
So the question is, can we do something where we strengthen NMOS in one and strengthen PMOS in another? That will work for one particular data value, right? But because you have to store either 10 or 01. See, symmetry has to be there in that sense, because you don't know what data is stored. But interestingly, we'll just see in a few slides, you can have asymmetric cells which help to solve the problem, but in a different way. But you can have asymmetric cells. They have been proposed. So before we do that, let us look at the layout of this cell. Okay, so again, as I said, for SRAM's layout is very important. So how do we understand this layout? So what we have is, we have these what are called flat cells, thin flat cells. Okay, so this is one inverter. This is the second inverter, this one. Okay, so this is the PMOS. This is the gate. So remember, the PMOS and the NMOS. So that is what is happening. You have source and drain, source and drain. Okay. Now, if you see from here, the drain, this is the access device, because the inverter's lower NMOS transistor is the driver device. And the driver is connected to the access. So that is done just by extending this diffusion, and then you have the word line here, so this becomes the access. These blacks are the contacts. And if you see out here, they show half contact, because it's just to show that it's shared. Contact will always have to be full square, but the remaining square piece of the square is on the next cell. It's accounted as the area for the next cell. So the area accounting basically does it like this. And the other thing you see out here is the gate, because you also have this cross coupling. The output of one becomes the input of the other, and vice versa. So the output of this inverter, so let us say this PMOS and this NMOS, the output, these two are connected by metal. It is not shown in the figure. Similarly, these two are connected by metal. It's not shown. And this output is directly connected to the gate. Similarly, here it's connected to the gate. It's a very nice layout. And what this layout does is, it reduces the height of the cell. Number one. Number two, all the transistors are horizontal. That is the second thing. Now, what is the impact of reducing the height? Because remember, the bit lines are going vertically. When you reduce the height, the length of the bit lines go down. So capacitance goes down. So it helps from a speed perspective. Because what drives the bit line during a read is the cell, and the cell is very weak. So whatever you can do to help improve the speed is good. Of course, you have increased the horizontal. But the horizontal is word line, which is driven by an inverter. You can easily scale up the size of the inverter. There is only one inverter per row, whereas you don't want to increase the size of the cell to increase it. So this short, wide layout is now the standard layout structure which is used, right? The second thing is the orientation is all the same. That is also very important from a variability perspective, because it turns out that a vertical transistor and a horizontal transistor will, even though they have the same width and length, everything is the same from your design perspective, they will have different characteristics. So whenever you want to match transistors, you want to have them oriented the same way. Okay. Now, what are the transistors you want to match? There is a certain relationship you want to maintain between the strengths of the driver and the access. So previous layouts, which you can look up in the textbook, the driver transistor and the access transistor orientations were different. Okay. But here they are in the same direction. Similarly, PMOS is also in the same direction. So all this basically helps to make it much more, everything kind of is related to everything else. So the variation kind of effect comes down. Of course, when you put in these two extra transistors for the 8T cell, this is called an 8T cell, your size goes up because you have to put these two extra transistors. Now, why would you want to use this? It turns out you want to use this under certain conditions when your read noise margins have really become poor. That happens when you are operating at much lower supply voltages than what you normally should be. Maybe there is a special application. Remember, we talked about sub-threshold operation. Maybe you want to operate at very low voltages. So at that time, the first thing which fails is the memory. So you have to do extra things to look at the memory. And remember, when we say failing of the memory, we don't mean, we are concerned about failure of the memory when you have like millions of these cells. Maybe one or two cells might, you want to ensure that the yield of a memory cell is very good. One cell might work well in your simulation, but you're looking at the whole ensemble of cells across your plus minus 5 sigma variation should work well, should have good noise margins. At that time, you basically look at these alternate structures, right? When your read noise margins are poor, because you have current going through the cell, you look at these other ideas.
So with
Yeah.
previous diagram, the new arrangement is being used, then one of the access lines, can it become redundant?
We'll see, right? So the question is, will one of the access lines become redundant? That's a good question. We'll see how when we do write, we actually need both of them. Okay, for writability of a cell, for proper writability, you need both of them. But there is a way you can remove that, but you have to change the cell. But for this 6T cell, you need both WBL and WBL bar. You need both of them. The reason is basically, if I want to write into a cell, I have to push a 0 into the cell. So if I want to write a 0 here, I need to push a 0 through here. But if I want to push a 0 here, I'll have to push a 0 from here. Remember, because I can't push a 1 here. Pushing a 1 through NMOS doesn't work well, because NMOSs have this threshold drop, right? So you really write a cell by pushing a 0. And then you have to push because the 0 can be here or here, you have to have ability to push a 0 from both sides depending on the data you write. So you need to have both the bit ones. If you remove this, then if you have to be able to push a 1 or a 0 from both sides, which means you need to have a transmission gate. So that is possible. Okay, so here is another idea. This leads to an asymmetric cell. Okay, the reason I'm kind of showing this again is basically just to illustrate the point what people are doing. I mean, how you can take this concept. The basic idea is to not, the bump during a read of on the 0 side causes a tripping of the inverter. So one approach was, let us say this is 0 and this bumps up. One approach was, don't let a current go through this. That is why you put the read buffer. This other approach, what they do is, they say let the current go through it, let it bump up. But when it bumps up, what happens to this inverter? He has to his NMOS discharges the output, and that is what causes the cell to flip. But what if you prevent that NMOS to discharge the output by putting an additional transistor which you turn off during a read? So that is what is done. During a read, when word line goes high, word line bar goes low and it turns off. So now even if this guy bumps up, nothing happens because I cannot discharge it. Remember, this is at 1, this is at 0. I read and this starts going up, but then it's okay because I cannot discharge it because this is shut off momentarily for the duration of the read. Okay, so but this leads to an asymmetric cell, and it kind of looks strange. There is no symmetry, but then they have been able to do a nice layout and so on, and show. That's why they call it read SNM free SRAM cell. That means there is no problem. The read noise margin is the same as hold noise margin. In fact, they say there is no issue of a read noise margin because you just disconnect this. There is no way I'll flip the cell.
This can serve in to reduce the bump in the right side input. Output of right side input.
Correct. Only because the read is only done through this cell. When I read, what they do is they don't turn on this. Remember, this is right word line, read word. Read word line is connected only to this transistor. So you never turn on this side during a read. You only turn on one side. Okay, now if the data is 0 is when we said we could have a problem of flipping the cell, because when the data is 0 here, I have a current flowing through here which can cause this go up and bump, but that is prevented by this. When this is 1, there is no issue because bit line is also pre-charged to 1, this is also 1, there is no current. You wait for some time, if the bit line is not discharged, you just call it a 1 and go ahead, right? So the way you sense a 1 is, you give us some fixed amount of time and then you sample the bit line. If it is not discharged below a certain value, you say it is a 1. If it discharges, then you say it's a 0. So again, you can, if you are interested to know more about this, you can read this particular paper in this Journal of Solid State Circuits. These are things not there in a textbook, but I thought it's just interesting to for you to just become aware that how people, various ways in which people try to solve these problems. So I'll just quickly flash through these and then I'll come back again in the next class. Okay, maybe you might not, that may not become fully clear, but let me just introduce these. There is this concept of soft errors. Okay, soft errors are errors where there is an error which happens, but it doesn't damage the hardware. So, but there is an error. So, for example, these errors happen because of ionized radiation, which hits your chip. Right? When these ions hit the chip, heavy ions, basically ions hit the chip, you have electron hole pair created because they go and break the bonds or essentially, cause carriers to be generated. So, as soon as these ionized particles hit, you have a little burst of charge. And remember, in CMOS, all information is essentially stored as charge. So when you have extra charge which comes in, so the amount of charge which is generated depends on the kind of ions which come in. Okay, and different ions have different what is called rate of charge creation. And if the ion is not too energetic, of course it doesn't create. But if the ion is very energetic, it also goes fast, so it just goes out also very quickly. So there are certain energies which are bad in terms of generating the most amount of charge. Now these kinds of charges can lead to hard errors. Okay, for example, you can puncture your oxide. The oxide, maybe you damage the structure and some charges trap and the threshold voltage shifts, or maybe you have now leakage through your oxide. So those are hard errors. When that happens, you can't do anything. Right? You take your chip close to a nuclear reactor, close to the core, it will just, it will get damaged. Soft errors are errors where that kind of damage doesn't happen. Charge gets created and then it perturbs or changes the state of the circuit. Because your circuit is all Essentially, you have essentially a sea of capacitors which are charging distance. But this error can be pretty fatal and catastrophic. Your whole system can mess up. Right? So you are depositing your money into your bank account. At that instant, soft error changes some bit, money goes to your bank's account. Okay, so that is a catastrophic error. So these errors are very. So now you would say, these ions and so on, are they so important? Why should we worry about it? If you do some space-based application, okay, you can understand. But no, it turns out that even under terrestrial conditions, now actually, especially some of these materials used for packaging and so on, they can have these heavy elements which can release ions and alpha particles and so on. And also, of course, you have cosmic radiation coming in. So we are always bombarded by these things. And as you are scaling down, the transistors and devices have become more susceptible, and especially memories. And that's why I'm kind of discussing it now here. And the thing is, the way this when you have the ion go through, you have suddenly a burst of charge created. And remember, what we are showing out here is the diode, the source and drain diffusion region. We are just looking at that region. So you have this burst of ions created, and then the electric field pulls in and separates out the charges, and then eventually there is some leftover charge kind of drifts and it diffuses because of concentration gradient. So if you look at the current profiles, there is a peak of current, and then slowly the current decays. And this will lead to an error. It's called a soft error, and the rate of error depends on the area. Clearly, of this is called area of the diffusion. If you have large diffusion, you have more charge created. Okay, so there is more chance for error, which of course you want large diffusion if you are doing a detector for these ions. Okay, maybe you are doing a detector to detect these ions for these colliders and so on, or maybe you are doing a detector to catch light, CMOS images. So you want large areas, but otherwise you want to keep these areas small. And there is also critical charge, which will cause the node to trip and change state. So that critical charge is important, and I'll not kind of go into this Q collector, but basically there's notion of a critical charge. If that amount of charge gets created, then the node will flip. Okay. So usually you measure this in terms of failure in time of billion hours. Over a billion hours of operation, and how many billion of hours does it take to fail? That is, the time is measured in units of billion hours, and the mean time to failure is inversion of that. So 1000 FITs means about 114 years. As you have more and more components, you have quicker time to failure. When you have billions and billions of SRAM cells, each cell has a certain mean time to failure. The overall SRAM array will have a much lower mean time to failure. Now, why is this important? This study basically shows that one thing is that as you are scaling the technology, remember we are going from, now we have about 45 nanometer, 32, 22, 16, etc. The capacitance reduces because everything is made small, which is good for area. You can put more things, but each thing now has much smaller area and hence can hold much lower charge. So if the circuit node has lower charge, then what the Q crit is actually coming down. Lesser amount of spurious charge can change the node. Not only the capacitance going down, we are also reducing the supply voltage, right? Because we wanted to keep power low, as well as as we reduce the dimensions, we don't want large electric fields, so we reduce the voltage. So both of these are causing the Q crit to start coming down, and so now there is more chance for failure. Okay, that is basically what the voltage is reducing, volume is reducing, capacitance is reducing. Okay, so what people are of course doing is that, now this is also a problem in the case of DRAMs. Imagine for DRAM it is even worse because you have only floating capacitors in a dynamic RAM. Okay, we'll study that next. So in a dynamic RAM, what people do is, even if you shrink that dynamic RAM, you try to keep the capacitance the same by using a lot of material tricks, high K dielectrics and so on. So the message out here might not be very apparent right away from these graphs, is that actually if you look out here, the even though for a single SRAM bit, the soft error rate they have managed to maintain somehow by various tricks. But overall, for the system of the entire all the SRAMs, all the SRAM bits, because in the system the SRAM number, then the number of bits in the SRAM is also going. So for the overall system, the soft error rate is going up. So because of this, when you put in an SRAM, and there are various ways of dealing with this. I will not go into all the details, but I'll just look at what you do in the case of an SRAM. Is you add redundancy. So really the way to deal with soft errors is to add redundancy. Physical level redundancy is increase the amount of charge stored. When you increase the area or increase the voltage, you're having more charge stored. So that is in some sense a redundancy. You can look at various layout structures, etc., etc. But at the next level, system level, redundancy is to add extra check bits. So for example, one extra bit for even parity, parity check. You can have, if you have n bits, you can add k extra bits such that Hamming distance is maintained, at least 3. That way you can correct single bit errors, detect double bit errors, and so on. And you can interleave words, because when a strike happens, so what you do is you have the bits of 2 words, they are interleaved. That means bit 0 of word 0, bit 0 of word 1, bit 1 of word 0, bit 1 of word, etc., etc. Because when a particle hits it, it is going to corrupt neighboring bits. If the neighboring bits are all from different words, what that does is you have spread the error to multiple words. So instead of a single word having multiple bit failure, you have many words having single bit failure. But single bit failure you can correct by some simple things. So you cannot do things like that. So these are things which are routinely done. It used to be done in, now you can, for example, have ECC DRAM, right? Basically, when you buy those, you have extra DRAM chips which have these storage for these extra parity bits. And you can do this correction, single bit correction. But even within the chips now, SRAMs, large SRAMs, people have started to put ECC in them to deal with this problem. Any questions?
So is that only single parity coding system only is being used, or any complicated coding system?
Basically what they do is, usually what is called SECDET, single error correction, double error detection. That is what is used. But for something like Flash and so on, more complex coding is used. Like these Reed-Solomon codes and other codes for burst errors. Similarly for hard disk, of course there we are not dealing with soft error problems, but you will have failures, or bursts of bits can fail, so you have to use more sophisticated codes.